Okay.
Hello, everyone. It's my great pleasure and honor to present Professor Andrei Osipov. Today, Professor Osipov is going to talk about inverse spectral problem and Volterra type lattices. Professor Osipov, thank you so much for accepting our invitation and being with us today. You may start whenever you're ready. Thank you so much.
Thank you. So first of all, I would like to thank in turn the organizers for an opportunity to give a talk. And my today's talk is a sort of introductory talk into my activities related to inverse problems. And I'd like to note that it's in line with December's talk on discrete inverse problems by Professor Yurko, and I'll concentrate mainly on the application of some special inverse spectral problem for the integration of some certain nonlinear lattices, nonlinear dynamical systems named nonlinear lattices, and as an example, I've chosen Volterra lattice. So partly my talk is based on these three papers, and in addition, I added the paper number 4, which contains some useful introductory information for Jacobi operators and in particular theory of extension of Jacobi operators. So mainly I'm interested in studying the relations between the operator theory and inverse spectral problems may be regarded as an integrable part of operator theory and the theory of integrable systems. So nonlinear lattices are nonlinear integrable systems, and mainly these relations are based upon the integration of nonlinear equations by various inverse problems methods. But I would like to say, so the development of this approach, of this method, inspired the development of inverse problems with the aim to cover wider classes of nonlinear equations. And also, I'd like to say that the integrable systems, some issues in that theory, have an impact on the operator theory, on some issues in operator theory, which lays apart from inverse spectral problems. Actually, the paper number 2 in my list contains some examples about that. So now I would like to say a few common words about the inverse about the integration by inverse problems of nonlinear equations. So 55 years ago, in 1967, Gardner, Green, Kraskell, and Miura discovered a method for solving the Cauchy problem for Korteweg-de Vries equation, that this nonlinear partial differential equation for real x and t, by using the inverse scattering problem for one-dimensional Schrödinger, or often called Sturm-Liouville operator on the whole real line. This Korteweg-de Vries equation admits the lax representation, so it can be written in this form. Here, the square brackets stand for commutator. L is the Schrödinger operator, and A is a skew symmetric differential operator, which is this one. And the general scheme of their method is the following. So from the initial data, we construct the Schrödinger operator with potential to 0. Then we calculate the scattering data at 0. Then, according to the Lax equation, we find evolution in time of the inverse of the scattering data. And then at time t, we reconstruct the potential by solving inverse scattering problem. And this reconstructed potential gives us the solution of the Korteweg-de Vries equation. So it's quite a brilliant scheme. Sometimes it's called that integration via Lax pair formalism. And a similar approach is applicable to another nonlinear partial differential equations. As a matter of fact, for nonlinear Schrödinger equation, instead of Lax equation, the so-called nonlinear curvature equation is used. For nonlinear differential difference dynamical systems, that's with the discrete spatial parameter and continuous time, such as Volterra lattice, Toda lattice, and Bogly-Gavlensky lattices. Hopefully later on I'll mention them all. Nonlinear difference equations. So it's a discretization in time and space, and cellular automata, some objects from theory discrete mathematics, which that approach also can be used. And now let's proceed to Volterra lattice. So Volterra lattice is the set of ordinary differential equations for functions AI described as follows. Here it's AIs times AI plus 1, AI minus 1. So AI t are some functions. So the lattice is called infinite if i's are all integers from minus infinity to infinity, semi-infinite if they are non-negative integers under additional condition a minus 1 equals to 0, and finite lattice if the indices I are from the finite set. The alternative names for Volterra lattice are Katz-van Merbeke system. Actually, Katz and van Merbeke about 50 years ago started to study that Volterra system, and it was their suggestion to call that Volterra lattice. Also in connection with plasma physics, because this equation is the transition equation for Langmuir waves in plasma. So they have application in plasma physics, and it was studied by Monakov and Zakharov approximately at the same time. And they also showed that it might be considered as a discretization of Korteweg-de Vries equation. So the alternative name for it is discrete Korteweg-de Vries equation. So there are all four names are representing more or less one system. And I would like to say a few words why Volterra lattices. So Volterra studied biological models in addition to his numerous activities in other areas of mathematics. So finite Volterra lattice may be regarded as a special case of the generalized Lotka-Volterra equation describing predator-prey interactions for a sequence of biological species, which each species preying on the next in the sequence. So suppose we have some lake closed space populated by 3 predators. Sharks, the biggest one, perches, some average predator, and piranhas, quite small ones. So then their interaction can be described by this system. So sharks are eating perches and piranhas are too little to them, and their evolution depends on the amount of perches they meet. So the second equation is the evolution of the perches. So they are eating piranhas, shows that AI times A2, and in turn they are themselves a food for sharks. So minus A1, A0. And the third one are piranhas. So they are only food for purchase and no other objects to eat. So quite a good family. And now let's proceed to the case of semi-infinite Volterra lattices. So here i's are non-negative integers. They are non-zeros for t from 0 to infinity. And it's of our special interest to study this system in the class of bounded solutions, such that for each t, that bit are forming the bounded sequence. So they belong to the space L infinity for all t. So first we go to the Lax representation. So this, like the Korteweg-de Vries equation, this system admits the Lax representation, which is with this matrices L and A. As we see, L is a three-diagonal non-symmetric matrix with 0 main diagonal, and the operator A is a lower triangular part of the square of matrix L. So if we multiply L by itself and take its lower triangular part, we get the matrix A. And this Lax equation gives a start to Volterra hierarchy. So a family of nonlinear lattices with the same matrix L and more advanced matrices AM. So the matrix AM, it's the matrix L in power 2m, and its lower triangular part. And V1 is the original Volterra system. Actually, it was an interesting task, and I tried to solve it unsuccessfully to show that as I said, the original Volterra lattice may be regarded as a discrete Korteweg-de Vries equation. And the original Korteweg-de Vries equation also gives a start of the hierarchy of Korteweg-de Vries equations. So, and I tried to show that the higher Volterra systems are the discrete analogs of higher Korteweg-de Vries equations. So, and then it was shown by two Italian authors, Morosi and Pizzocchero, in late 90s. Then some linear combination. Some linear combination of these lattices may be regarded as discrete analogs of higher Korteweg-de Vries equation. They used an interesting approach from theory of integrable systems based upon Magri's big Hamiltonian formalism, and I just tried to prove that straightforwardly. And so that higher linear combination of higher Volterra equations may be regarded as discrete analogs of higher Korteweg-de Vries equations. And now let's proceed to the inverse spectral problem for operator L. But here we have just an infinite matrix, so we must proceed from the matrix to operator. And first, we have to define an operator L. At each moment t, we identify the matrix L with the non-symmetric operator defined as the closure operator acting on the dense set of finitely non-zero, that's a little mistake, finitely non-zero vectors from L2, the Hilbert space of complex quadratic summable sequences. So here, where the action of this operator is described via matrix calculus. So if we have an vector from L2, it is an infinite sequence, quadratic summable, and the action of operator on this vector, it's just a multiplication of matrix L onto that infinite sequence, no more, no less. That finitely non-zero vectors from L2 are forming a dense set from L2 in L2. So this operator admits a closure. And we identify the matrix L with the operator L. Keep the same notation, this operator. Also, we need two notations En, the standard orthonormal basis in L2, and omega L, the resolvent set. And then we proceed to the main objects in our approach, the Weyl solution of L and Weyl matrix of L. So by Weyl solution for lambda from resolvent set of L, we define the functions pi forming the Weyl solution like this. So in fact, it's just a resolvent of operator L applied to the vector E0, and pi's are just its components. E is identity operator, and we define the resolvent like this: lambda E minus L, and the inverse of that operator. In other words, P lambda satisfies the matrix equation. And if we write this equation component-wise, we see that pi lambda satisfies some difference equation. And in that sense, it solves it. So the word solution is justified. So it solves this equation. And the Weyl matrix, or the Weyl matrix of L, here it's actually Weyl function. It's the simplest case of Weyl matrix, it's Weyl function. It's defined as the first component of the Weyl solution. Here it's by definition, and here it's R00. If we have a matrix representation of R lambda, then its component with indexes 0, 0, it's the Weyl function of L. If the operator L is bounded, then for absolute values of lambda greater than norm of L, the Neumann formula for its resolvent is valid. It's that resolvent is represented as the power series with the powers of L. From this formula follows the formula for components of pi I lambda for such lambda, as we remember that's and in particular the Weyl function is defined like that. Sk are the elements of kth power of matrix L with coordinates 0, 0. So, and this allows us, and actually this representation is for bounded operators L. But we can, in general case, consider the formal asymptotic expansion of the Weyl function at infinity with this parameter, with this coefficients sk. So this allows us to make the following general definition. So the sequence S equals sk from 0 to infinity, where sk is defined as follows, is called the moment sequence of the Weyl matrix of L, and the elements sk are its moments. So we can formalize our inverse problem as follows: given the moment sequence, find the elements of L from one to another. And now, for better understanding, I'd like to a little bit step aside and consider the inverse spectral problem for classical Jacobi operator. Namely, consider the semi-infinite Jacobi matrix. So it's three-diagonal matrix. The right and left diagonals are positive numbers, and B's are real numbers. So such matrix, in the same manner as above, generates this symmetric operator. but not necessarily self-adjoint. So actually, there might be two options. The deficiency indices of this operator might be either 0, 0, then it's essentially self-adjoint, or 1, 1. In that case, we need to get its self-adjoint extension. So the a spectral function of this operator is defined as follows, where E lambda is the spectral measure of its certain self-adjoint extension. And inverse spectral problem for classical Jacobi operators can be formulated as follows: given rho lambda, the spectral function, and find the elements of L. And it's solved as follows. We have the sequence of powers of lambda, like 1, lambda, lambda square, and so on. And we apply the standard orthogonalization procedure with respect to the d rho lambda, and we find using this procedure, we find polynomials bi lambda, which are orthogonal by d rho lambda, and then we get the coefficients ai, ebi by these formulas. And for the moments of the spectral function, actually all moments of such spectral functions are finite. So for the moments of the spectral functions, we have, using the spectral theorem, the following results. So Sn equals to nth power of matrix J with coordinates 0, 0. So they are calculated in the same manner as in our case for the operator L. And the Weyl function of J is defined as this, it's called the Stieltjes transform of the spectral function. And again, according to the spectral theorem, it may be written as that resolvent of operator J applied to E0, and that's scalar product with E0. And we can again apply the Neumann expansion to the resolvent as above, and get the asymptotic expansion at infinity with these coefficients S1, S2. They are the same moments as here. And we denote as delta n determinants of the Hankel matrices composed of the moments. And then for that polynomials bi lambda, it can be checked that they satisfy this equation, polynomials. And using and substituting the formula for these polynomials here, we get the equations for coefficients ai's and bi's. So what I want to say, that from the inverse problems point of view, the object, the spectral function, and the spectral function and the Weyl function are two equivalent objects, and all they need from them to find the coefficients of the matrix J are the moments. In one case, they are just integrals of powers of lambda, and in another case, coefficients of asymptotic expansion at infinity. So there are two equivalent objects, and that's somehow the spectral inverse. The word inverse spectral problem is justified in our case as well. So now we proceed to the solution of our inverse problem. Actually, it's a very special case of the inverse problems considered in December's lecture by Professor Yurko. And here, operator L is non-symmetric. And I'm even so there is no spectral function, no self-adjoint extensions, no spectral measures. But what can we actually take from the classical case to our case. Here there is a three-term recurrent relation or second-order difference, finite difference equation associated with operator. And in our case also there is a second-order difference equation associated with our operator. And there exists so-called Favart theorem, or in some sources it's called Shochat-Favart theorem. So if we have polynomial solutions of a three-term second-order difference equation with certain initial conditions, then there exists a functional such that these polynomials are orthogonal with respect to this function, and the Weyl function, Weyl matrix, or to be more precise, their moments give us that functional. So it works in the non-symmetrical case as well. So we can use that orthogonality to obtain that coefficients bi's, which are and bi's in our case will be almost the same as in the classical case, except that there is no square root, and the coefficients bi's are calculated as follows. And also we need to establish a criterion of the inverse problem, for example, in terms of the moment sequence. So we have a certain sequence of complex numbers, and this sequence is the moment sequence of the Weyl function, in our case of a certain operator L, if and only if. So the first element equals to 1, its normalization condition. Then for all complex i's, determinants delta i's are non-zeros. That's the central condition in that criteria. And also the third condition, it's a sparsity condition, which says that all odd moments of the matrix L are 0. If we remember here in our matrix L, the main diagonal is 0. So that third condition gives us the criterion for that. All odd moments are 0. So that's the solution of our inverse problem in that simple case. And now let's proceed to the integration of Volterra lattice. So first, from the Lax equation follows the equation for the resolvent of operator L. That's actually for every operator which satisfies the Lax equation thoroughly. And then we remember that the Weyl function, it's using the matrix representation for the resolvent. It's just its element with indices 0, 0. Then we substitute here instead of the infinite matrix R and also infinite matrix L, and find the equation for M. And also from the matrix equation, which is just follows from definition of the resolvent, it's the inverse operator to this one. And we are writing that in the matrix form and component-wise. We get two equations from which we find the expression of R02 in terms of R00. And we obtain the evolution equation for the Weyl function, this one. Also, we can note that S2, that B0, it's just the element of matrix of square of matrix L with coordinate 0, 0. We just can multiply the matrix L by itself and get its element with coordinate 0, 0. And also we, as we remember, the moments corresponds to the coefficients lambda with negative the negative powers of lambda. So this element minus lambda is out of the game, and here lambda square means that we have to take s chi plus square. So we get this evolution equation for the moments. This actually means that if this system has a solution, then the corresponding equation for the moments is the following. And this equation can be written in the equivalent form as an integral equation. It's also quite simple to check. So if we take this equation and if we differentiate it, then we get this equation. And then where xt is the solution of ordinary differential equation with this initial condition. And then if we assume that bit are all bounded for all t, then after solving this equation by iteration, we get this solution for the moment. So it's representation of infinite series. And also we can prove local existence and uniqueness theorem for the system 1 in the class of bounded solution. So in view of all these results, we are arriving at the following theorem. So for each set of initial complex data, which are non-zero, there exists delta greater than 0, such that the Cauchy problem has a unique solution, which can be found in the following way. So using L0, we construct the matrix L0 and find the moments at 0. So it's our inverse problem data at 0. Then calculate the moments at time t according to this equation, which we just above established, and then using this formula, we calculate the coefficients bi's, which give us the required solution at interval 0 delta. It's interesting question about the global bounded solution, and it was shown not by myself that if the initial, for actually more advanced nonlinear lattices, that if the initial data are non-zero and all positive or all negative, so they are all of the same sign, then such a global bounded solution exists for all t. And this is a non-trivial result, which requires the use of the moment problem and theory of rational approximations. But I would like to say that the question for each initial data, there exists the global solution for all t, even for Volterra equation. For to my knowledge, it is enclosed. So, for example, if there is one change of sign in the initial data, even if they are all real, can we find some global solution or not? I don't know. And I'd like to also say about the finite lattice case. So if we consider a finite lattice, here instead of the semi-infinite matrices L and A, there are finite matrices L and A, and here is a finite matrix L, we call it Ln. And in this case, the moment sequence, which corresponds to finite lattice, has two features. So the first, so for the moment sequence, which correspond to the finite lattice, there exists some constants such that senior moments are linear combination of the junior ones. In this case, there are n plus 2 numbers. And if we construct an infinite Hankel matrix composed of the matrix. In this case, its rank is equal to n plus 2. And in semi-infinite, for semi-infinite lattices, its rank is infinite. So for the finite lattice, in that case, delta I is equals to 0 for I from 0 to n plus 1, and delta n plus 2 equals to 1, 0. That's the specific of the finite case. And also for the finite Volterra lattices, that quantities which are coefficients in the linear combinations are first integrals. So their derivatives by t equal to 0. And as an example of application of our method, we consider another lattice. It's called finite Bogoliablensky lattice. Here, if we compare this lattice with Volterra lattice, we hear that AI square instead of AIs in case of Volterra lattice. And this system admits the Lax representation with this operator A and operator L. And here, as you see, the matrix L has a peculiar form. It's 2 diagonal, and here is 1. So it's, actually, so I would say that it's quite unclear how to solve it by straightforward application of Lax formalism. But instead, we can solve the Cauchy problem for this finite Bogoliablensky lattice by using the auxiliary Volterra lattice. So if we set B0 AI plus 1, 0, then we can consider the Cauchy problem for the finite Volterra lattice with this initial data. Then we can solve them. And then by setting A0 and AIs like this, we get the required solution of the finite Bogoliablensky lattice with that cubic nonlinearity. And this theorem actually says that. And also another application of this approach, it's the interaction between Volterra and Toda lattices in the semi-infinite case. As you remember, I showed the Volterra hierarchy defined like this. And we also can consider the Toda hierarchy of Toda lattices given by that Toda lattice in the semi-infinite Toda lattice given by this system of equations, and it also admits the Lax representation with this matrices L and A, and also it gives start to hierarchies of lattices. And for Toda lattice, we also can introduce the Weyl function and its moment sequence, and we denote S and tilde S the moment sequences of the Weyl functions of operators L and L tilde corresponding to Volterra and Toda lattices. And the equations of Volterra hierarchy can be mapped into their Toda counterparts by using the Murat transformation given by these two formulas. And this theorem gives us a description of Murat transformation in terms of the moment sequences S and S tilde. Actually, it might be interesting in studying the finite integrable systems or finite lattices, because that transformations, Murat transformation transforms all objects of interest of theory of integrable systems, like first integrals, master symmetries, Poisson brackets, Hamiltonians of one system to another. And this equation, this transformation actually, in case of Toda and Volterra lattices, it doesn't lead to some non-trivial first integrals, but in case of another lattices, it can give some non-trivial first integrals. And also such transformation is valid, such description of Mura transformation is valid also for classical Jacobi matrices, which used for integration of classical Volterra lattice with positive coefficients and classical Toda lattice. And this transformation allows us to establish a bijection between classical Volterra lattices and classical and Toda lattices, which are characterized by positivity of the operator L in its last representation. And my paper number 2 contains that result from that list. And another generalization of this approach is Bogoyavlensky lattice. So for p equals to 1 in both systems, it's the above considered Volterra lattice. And actually these two lattice the above considered approach is applicable to both generalizations of Volterra lattice. And here, instead of Bail function, there are Bail matrices. In one case, here it's a column. Yes, it's a column matrix 1 times p times 1, and in case of the second equation, it's a row matrix. It's 1 times p. It's p times 1. And also the approach is applicable to non-abelian lattices, the lattices with matrix coefficients. As a matter of fact, the infinite, for example, infinite Toda lattice or infinite Volterra lattice may be transformed to a semi-infinite case with matrices 2 by 2. It's just a very simple and straightforward application of non-abelian lattices. So that approach works for that system as well. And here it's the Bogoyavlensky lattice with cubic nonlinearity, similar to the considered, where is that? Yes, similar to this one, but with matrix coefficients. But here, the inverse problem for that finite system is different from the above considered one, and there is no orthogonality, so we can exploit only the Weyl function and the behavior of its moment. And actually, I hope that once quite soon, another paper of mine will appear, which deals with that special case of Bogoyavlensky lattice. So I think, yeah, I think that will do for now. Thank you.
Thank you so much, Professor Osipov, for the excellent talk. Any questions or comments, anyone?
You see, I have 2 questions.
Yeah.
The first is the following. Many years ago, approximately 1995, 96, yes, I published several papers.
Yes.
Unfortunately, I forgot the formulations of the main results exactly. But what I remember, today I tried to find my papers. I found them, but I had no time to remind. Unfortunately, I forgot a little bit, but what I remember. I remember that I considered inverse problems not only for Jacobi operators, but for high order difference operators, and
Yes.
also
It's
for
like in this case.
yeah. And also very generalization, the so-called air structure. And inverse problems were solved for this general classes. I remember this. And solved means not only algorithms, but also necessary and sufficient conditions.
Yes.
And then I also studied dynamical system.
Yes.
Dynamical systems, it was that time. And the
1995 approximately.
dynamical systems were in very general form.
Yes.
And this how to say it, this method using the inverse how to integrate this nonlinear dynamical system using inverse spectral problems. This method was used, and in order to solve such a nonlinear system, I use the inverse problems for higher order equations, for air structure, and of course, in particular case, for Jacobi.
Yes.
And my question is the following: can you compare your result with mine? Maybe I try to explain my question in more details. You see, since I consider it higher order difference equations, and of course, Jacobi is a particular case.
Yes.
So all dynamical systems which connect with Jacobi operators were studied. So I don't remember exact statement of my results, but it seems to me that since you use Jacobi operator, then your system must be a particular case of mine. Is it true or not?
Actually, it's question of the class in which the solution of the system is looking for. If I am correct, that in your paper you considered the complex solutions which are non-necessarily bounded, and got some general result for Todd-like lattices, and you get some results about the solution for generally not necessarily bounded case. And here I restricted to the study of bounded solutions. And in case of the bounded solutions, in terms of the differential equations, so generally it's a local solution, and the global solution, as I said, might be global bounded solution, might be established in some specific case, like all initial data are of the same sign, and I don't know. So for which exact initial data there exists the global bounded solution for all t. That answer to this question, so far I don't know.
But you see, if you study bounded solution,
yes.
But I studied arbitrary, so
yes.
my case is more general. If I got the algorithm for arbitrary situation, in particular, I got an algorithm also for bounded. It's automatically, because bounded in a particular case. You see, if you see, there are two situations. If someone wants to get only algorithm,
yes.
Then of course, if someone got an algorithm for more general situation, this algorithm automatically works for less general, for particular cases. But there is another problem, necessary and sufficient conditions for the solvability. The situation there a little bit different. Sometimes if I got, for example, necessary and sufficient conditions for more general object, sometimes using specific of the structure, necessary and sufficient conditions for particular case may be quite different. So in this case, it's not possible to say that if I got results for more general situation, it's automatically works for less general. But if we study only algorithms, it's really true. If I got results for more general, but I got really, then for particular cases, this algorithm automatically works, and for bounded too. Is it true?
Yes, from that point, yes, I think that is true. So the algorithm might work in the bounded case as well. It's true. Yeah.
But this means that your results is a particular case of my results.
Well, actually, it in more or less in the same sense that the results in inverse problems is a particular case of results of R structures, which you proposed. Triangular structures, sorry, triangular structures as well. But each specific case has its own peculiarities.
But since you have you did not study the necessary and sufficient conditions, and you study only algorithms, that this means that these results are particular case of my results.
Well, actually, I don't quite understand what you mean by necessary and sufficient conditions. So in case of that simple inverse problem, it's that condition 1 and 2, these are exactly your conditions. It's in much less general setting. That is true. Only the condition 3, like sparsity condition, it's because of specific of the matrix L, which has 0 main type.
No, it's my question devoted to necessary and sufficient conditions for dynamical systems, not for inverse problems, for dynamical systems. But you see, it's okay. I understand. And my second question already, I wanted to ask about the not bounded solutions, but we already discussed this. So I have the second question. It's okay.
Thank you. Thank you.
I would like also to say about the last non-abelian lattice. Actually, it's although this lattice, the matrix L has very peculiar form, but it's also may be regarded as a special case of triangular structure. So in that case, even there is no orthogonality, like in the case of other lattices. It's also the approach based upon Weyl matrix may be used for its integration and for solution of inverse problem for such matrices.
Okay, thank you so much. Any other questions or comments? No, I guess. Okay, then. Professor Osipov, thank you so much for the excellent talk again and being with us and accepting our invitation.
And thank you for your attention.
You see, Andrei, I have a question about your work. You work in the Institute from Russian Academy of Science.
Yes.
And you have any lectures for students, only research?
Well, actually, for how many? 6 or 7 years, I have no lectures. I was a part-time teacher at Institute of Power Engineering, but attended in 1917.
Mm-hmm.
And since then, yeah, only that research work in my research institution with some computer works. And
By the way, do you need to go to the institute each day, or you can work at home?
now 2-3 days a week.
Понятно. It's
I'm
clear.
obliged to go. Yeah.
Clear.
Okay.
Okay.
Thank you so much again for
Thank
joining
you
us,
for your
everyone. And thank you so much, Professor Osipov, again. And see you next time.
Thank you.
Thank you.